Right here on our channel, we have lessons on giant covalent structures and Bucky Balls, fullerenes, and nanotubes. This lesson brings together a very important concept in chemistry explored in those two videos. The term allotrope refers to different forms of the same element. Right in our giant covalent structures lesson, you may have learned about the structure of diamond and graphite. These two substances are made of only carbon atoms, yet they exhibit very different physical and chemical properties. A diamond is very shiny, remarkably strong, and does not conduct electricity. Graphite is black, not nearly as strong as diamond, and can conduct electricity. These differences are due to the arrangement of carbon atoms within the structure. Each carbon atom in diamond is covalently bound to 4 other carbon atoms in a tetrahedral structure. Each carbon in graphite is covalently bound to 3 other carbon atoms in a trigonal planar structure forming hexagonal sheets. Some other allotropes of carbon include the Buckminster fullerene molecule and graphene. You can learn more about these structures right here. This allotropism also exists in other elements, such as oxygen, phosphorus, and sulfur. Oxygen can exist as diatomic oxygen, which is the form that we breathe in and is vital for survival. In this allotrope, 2 oxygen atoms are held together by a double covalent bond. Oxygen can also exist as ozone, which forms the ozone layer in the Earth's atmosphere. This ozone is extremely important because it insulates the Earth. However, it is slowly being depleted due to human activities. We have a lesson on that as well. An ozone molecule is drawn so that 2 oxygen atoms are held together by a double covalent bond, and the remaining linked by a single covalent bond. But the double bond electrons are in fact delocalized around the structure of the molecule. This is known as resonance stabilization. The same phenomenon is seen in a benzene ring. The next time you strike a match, have a look at the match head. The match head is usually red. This is due to the presence of red phosphorus, an allotrope of phosphorus. The phosphorus atoms in red phosphorus are linked in a polymeric chain. Matches made of red phosphorus are known as safety matches. In order to ignite, it must be struck against the striking surface on the outside of the package. Right before the introduction of red phosphorus, the match heads were usually made of white phosphorus, another allotrope of the element. These different colors arise from their different structures. These strike-anywhere matches could be struck anywhere for ignition, but since this allotrope of phosphorus is significantly more flammable, it was very dangerous to use and have been slowly replaced with red phosphorus. White phosphorus consists of 4 phosphorus atoms, held together in a tetrahedral arrangement. Some other allotropes of phosphorus also exist: black phosphorus and violet phosphorus. Sulfur also exists as many allotropes. The one that you're most likely familiar with is S8, octasulfur, a bright yellow solid. In this allotrope, 8 sulfur atoms are covalently linked to one another to form such a structure. Another solid allotrope of sulfur is hexasulfur, S6. Sulfur can also exist as a gas, disulfur and trisulfur. So far, we have only discussed allotropes of selected nonmetals. This allotropism also exists in metalloid elements and metals, which you can learn about in the next lesson of our series.